like to invite our first presenters, AMER AWWAD from FIU, to present the project he is leading, development of rapid in-situ testing for concrete deck durability. Dr. Awad?
Thank you, Dr. Mehrabi. Good morning, everybody. My name is AMER AWWAD. I'd like to present our project titled Development of Rapid In-Situ Testing for Concrete Deck. A little background, steel is used in pre-stressed and post-tension reinforced concrete. Exposure to chlorides causes corrosion in the reinforced steel in the concrete, while sulfates and frost causes degradation of the concrete. Chloride-induced corrosion in steel concrete is of interest to structures exposed to de-icing salts and marine environments. The methods to decrease the permeability of the concrete is to use lower to cement ratio and higher cement content mixes that will have a greater cement factor and lower porosity. Use of SCMs, including fly ash, silica fume, and granulated blast furnace slag, can reduce permeability since they generally have better hydration within the pore space. The methods of determination of chloride diffusion parameters is typically done by coring and laboratory chemical analysis. They are expensive and time-consuming. Alternate methods for new concretes involve bulk diffusion, electrical migration tests, and as well as concrete resistivity tests. The alternate methods we developed here at FIU quickly assesses the durability of hardened concrete material against liquid ingress. And the aim of this project is to establish a relationship that might exist between the method developed at FIU and the standard test methods, including freestall, RCP, bulk resistivity, and surface resistivity. If such relationship exists, a durability assessment of the concrete bridge elements can be achieved in 20 minutes with the FIU method. The FIU testing apparatus consists of a hydraulic test pump, pressure transducer, data acquisition system, and a test specimen holder. The apparatus is compatible of testing concretes, is capable of testing concrete's resistance to water penetration. The hydraulic test pump is a Rothenberger model RP50-S. It has a maximum pressure of 860 psi, dual isolation valves, a pressure gauge with a maximum pressure indicator, and an onboard test fluid reservoir, which in our case will be water as a test fluid. The pressure transducer is from Omega Engineering and it has a pressure range of 0 to 700 psi. The pressure data is collected by an Arduino data acquisition module that is connected to a laptop computer and is located in the pressure supply hose. The test specimen holder is comprised of two 1.5-inch steel pipe flanges with an EPDM flange gasket between the specimen and the top flange. The concrete specimen is secured between the two flanges via 4 steel bolts. The T on the top connects the pressure supply hose, which is right here, to a pressure gauge and a purge valve. The purge valve is there to let any air out that's in the system before the testing commences. In previous testing, the tests were conducted on both UHPC and normal strength concrete. 2 specimens of each type of concrete were tested. Each specimen was pressurized at 200 psi, and then the isolation valves were closed, and the water pressure in the specimen was monitored for 20 minutes. Here you can see a 3-inch diameter cylinder of UHPC and a 4-inch diameter of normal strength concrete. This is the test results we achieved from those 4 test runs. The blue and the red line up in the top are the UHPC. As you can see, the pressure did not degrade over the 20-minute period, while the normal strength concrete decreased on the pressure. The current testing we're going to be doing is using standard simple mix proportions for the concrete. Specimen water content will be varied from 0.4 to 0.6. We'll be doing tests with and without air entrainment. And we're going to vary the internal moisture content from oven dry, 75%, relative humidity, 95%, and soaked. We're going to be using number 5.7 and number 8.9 size aggregate to make the specimens. The aggregate will be either limestone, river rock, or granite. During the phase 1, we're going to identify how the water pressure test is affected by the concrete characteristics. The results from these small-scale lab testing will be used to calibrate the water pressure data to concrete material and exposure conditions. If the influence of the aggregate porosity, size, and internal moisture content on the water pressure drop will be assessed. This is the test matrix where we're varying the water cement ratio, the aggregate type, aggregate size, air entrainment, and internal moisture for the phase 1 tests. During the phase 2, we're going to compare water pressure test to the standard RCP and freeze-thaw test. The data will be used to correlate a non-steady state chloride diffusivity and freeze-thaw performance, time to damage by natural frequency and length change. Again, this is the test matrix for phase 2, the same, similar parameters. The freeze-thaw test will be conducted on the concrete specimens as per ASTM C66 and AASHTO T161. The RCP test will be conducted as per AASHTO T277 and ASTM 1202, C1202. The bulk resistivity tests will be done as per AASHTO T358, and the bulk resistivity will be done AASHTO TP119. Phase 3 testing will include a field application and demonstration of the system. The concrete mix design with various compressive strength will be made with material and environmental conditions considerations from results of the phase 1 and phase 2 testing results. The water pressure test will be modified to demonstrate application to cast concrete slabs of various thicknesses. And in the final report, we'll summarize experimental results and complete system design of the FIU system. The ABC UTC guide and a video presentation will be prepared that summarizes the methods used and findings reached during the project. One other thing I'd like to add, we are in the process of getting a patent on this system currently. This is a list of the co-PIs working with me, as well as a research assistant. And that's my presentation. Any questions?
Thank you very much, AMER. It sure looks very promising and a good method. There has been always a need for faster way, rather than waiting weeks and months, a faster way to have a measure for durability of concrete. So we have a few questions to go through. I myself, first let me ask the question that came in. Then I have another question. And I want to remind again that this method is going through the patent, or method is patented actually. So let me go through the questions that we received first. One asking that what concrete characteristic in terms of durability can be evaluated by the proposed technique?
Well, one of them is to do a quality. The concrete quality will be assessed. The high quality concrete will have low water to cement ratio and thus will have lower permeability, and thus will be better for corrosion durability. Therefore, it will have a lower water penetration, so we will have, similar to the results we saw in the HPC, we will not have a pressure drop, a significant pressure drop as other concrete, a weaker concrete.
Okay. And then next question is that how is freeze-thaw testing related to this test method?
Well, as freeze-thaw, it measures the air entrainment, and using this system, the penetration would, the greater the air porosity in the concrete. Once again, this will be indicated by pressure drop during the pressure test.
Okay.
Armin, can I jump in to elaborate on what AMER mentioned with respect to the method and what aspect of durability is going to be measured by this method?
Definitely, Dr. Azizi. But let me add my question. Maybe you can also elaborate on that side of it. So basically, I saw that there's some comparison going to be there, but how would this method be calibrated with the so-called durability? If you can, when you are answering that, can you please also elaborate on that?
Let me, of course, I mean, the PI and the AMER and Dr. Kingsley Law, that will be, they outline the scope of the work. But the method, let me, because I have looked at their proposal and have some information. So let me elaborate so people out there can a little bit relate to this. And I will give I believe we have a couple of minutes time. Maybe I can elaborate on this. The method actually, the background for this development of this method is kind of interesting and funny in a way. A major TV station called FIU, and they were interested to see how you can compare the durability of the ultra-high performance concrete with the conventional methods. And they wanted to assess this in 10 minutes. So what we did, and if you don't mind, I'm going to turn my camera on so that people maybe won't get bored a little bit. So
Please.
We looked at the different methods of the available out there, and we couldn't find, for our life, we couldn't find a simple method that could, in 10 minutes in front of the camera, to assess the two methods. Assess how durable the ultra-high performance concrete is as compared to the normal strength concrete. So what we did is later with AMER, we developed basically this method, which is really applying a pressure, water pressure to the surface of the concrete. You can do this on site, or you can do it on a cylinder, okay? And if I'm not mistaken, every 1 foot, basically 0.433 psi pressure is equivalent to having a 1 foot of water on the specimen. So if you have close to, let's say, 200 psi pressure, that would be almost like having the cylinder under the more than 400 feet of water. And what you do is that you monitor the pressure versus the time. In what AMER showed, basically, in case of the normal strength concrete, after the 10 minutes, you had about 1 inch of the fluid penetrating through the concrete. Whereas in ultra-high performance concrete, after 30 minutes, absolutely none. And you monitor the pressure versus the time. Now, what AMER and Dr. Kingsley are trying to do is relate this to rapid chloride permeability test results and the freeze-thaw. So if the relationship exists, basically, let's say it's like a calibration. For example, let's say a strain gauge, we calibrate against the voltage changes, right? So here you have water pressure versus time that changes, and then you have the results of the rapid coloroid permeability, and then you have the results of the freeze-thaw. Now, if we can relate those two and then say this type of a pressure versus time relates to this results from the freeze-thaw or the rapid coloroid permeability. Let's say, for example, if you get so much penetration in 30 minutes, that's, let's say, equivalent to having a concrete that is a 20 coulomb in terms of the RCP. So that's a function, that's a relationship that they're trying to establish. And of course, I think, like AMER mentioned, the method is patented, and if Dr. Lau and AMER are successful, then all of a sudden you have a method that you can go to the field and mount this device and measure the time versus the pressure, and then say, really, the equivalent rapid coloroid permeability number or the freeze-thaw number is such and such. So anyway, hopefully, that kind of explained a little bit.
Thank you, Dr. Azmin. By the way, whatever makes the process of either construction, evaluation, inspection faster, so by that actually goes into the definition of accelerated bridge construction. So, and this method fits very well in that definition.
And I think Dr. Kingsley Law maybe jump in on some of the other aspects of durability that he's looking at.
Hello, everybody. Yes, so I'm Kingsley. I'm working with AMER on this project. This project was interesting because it not only we're trying to see how it can be implemented to compare with some laboratory testing for quality control, but more importantly, it can be applied in the field. So we feel this technique can have some good application not only to identify quality control, material specifications and selection, but also in some of the field measurements. One of the most important parameters that we're looking at is going to be the air content of the system. So some of the test variables we're looking at is the effect of different types of aggregate, for example, from limestone to aggregate. They have very different porosity and different water availability in the system. We're looking at the effect of air entrainment as well, especially for northern states. We're looking at frost attack, freeze thaw. And so we feel that we want to look at some of the more important general material characteristics and how it may affect the parameters in terms of the pressure and the water introduction in the system. I do want to note that typically in the field, if you want to assess the corrosion durability, it involves taking cores of the system, and it's a tremendous amount of work having to take a boat out in the water, for example, drilling a core that's semi-destructive, going to the laboratory, processing that material into a powder, rendering it, and then doing the chemical analysis. So the hope is that this type of testing can reduce a lot of that, a lot of the waste that goes with that type of testing to give you the similar characteristics of the durability characteristics of the material. So we're excited. The project's ongoing. We're going to initiate the testing within the next week or so.
Okay, thank you, Dr. Lau. Dr. Lau, because you have, I know that you have dealt with ASTM standards and even developed new standards for testing or so. When we say, let's say we go to the field and use this method to measure durability, which is of course calibrated with your lab test results, etc. How many of these you need to do? Is one would be enough, or you have number of tests to do to make sure that your results are okay?
That's a good question, and I'll refer back to what is traditionally done anyways in terms of chloride penetration and coring. And so if you have like a bridge deck, for example, or a concrete pile or a column or footer, you have different regions that have different level of exposure. So the areas that are submerged, the areas of concrete that's in the tidal region, those in the atmospheric region, those with different levels of de-icing salt and washing off of the surface, it will have different values anyways. And so really you can't depend on one value. You really have to take samples from multiple locations. In terms of some of the material characteristics, in terms of, for example, distribution of the aggregate, that's something that we're very interested in looking at. For example, in our testing, we're interested in seeing the effect of the size of the aggregate and the type of aggregate and its porosity. For example, if the test head is about approximately 4 inches in diameter, for example, I think the distribution of the aggregate on that surface area can be important, and it's something that we want to address. And so hopefully we can refine that, determine what is the material like and some of the material characteristics that can affect the surface measurements. But in the end, it's important to take several readings, if nothing else, due to the exposure of that surface.
Yes, and I was thinking, Dr. Lowe, if, for example, because if you install this device on the surface of the concrete, first, probably you will need surface preparation or so, and then how would you limit the leakage of the liquid or loss of pressure other than, is there something there to tell you that that thing is happening?
That's an interesting question. In terms of surface preparation, we're hoping that it doesn't require a whole lot of surface preparation. In marine environments, you may have some fouling that probably needs to be removed. It can be important. For example, in terms of electrochemical measurements, we take half cell potentials, for example, that the skin, the surface layer can be important due to the level of carbonation that can affect those electrochemical measurements. In terms of the water permeation, I'm thinking that it may not be as significant as some of the other conventional electrochemical testing. So we're hoping that it can be minimized and that this can be applied wherever we can on different surfaces. In terms of leaking, I think I'll pass that to AMER. He's been developing the interface, how to lock that system into place. It can be challenging, especially in surfaces on the bridge where you may not have very good access or you have geometries that are difficult to bolt down the system. So AMER, I know you have some ideas on like the EPDM and different gaskets that you're looking at for the project. Maybe you can chime in as well.
Yeah, in the current configuration where we're testing the cylinders, we have an EPDM gasket that's in there. It's about an 1/8-inch thickness. That can be varied to a thicker material, but there will have to be some surface prep to it to where the gasket meets.
Yes, thank you very much, and thank you, Dr. Lowe and Dr. Azizin Amini, for your contribution.